Hi and welcome to the next lesson in the stack and the subroutines series. This lesson's topic is the local state. Objectives of this lesson. We will study the EBP register and its use as the stack base pointer. We will learn about functions' local variables and where to store them. We will understand the general structure of the stack during the invocation of functions in our program. We begin with EBP. EBP is the extended base pointer. It is a register of size 32 bits. As usual, it has a lower part, which is called BP, of size exactly 2 bytes. In earlier times, there was only the BP register. The EBP register came later as an extension to the 32 bits mode. EBP had an historical role. In the past, ESP could not be used to access memory directly. And for example, this kind of syntax, dword ESP plus 4, was not possible. In those times, the EBP register was used instead. However, these days, ESP can access memory directly, which means that this is going to work these days. As a result, we got a spare register, which we can use for whatever purpose we want. Usually, EBP is used to hold the stack frame. Let's begin with an example. We can see here some code of a function called SUMNOW. You don't have to get deeply inside the code. I can tell you what it does. This piece of code just sums all the numbers inside an array of numbers, an array of dwords. It is really basic. It just first zeros EDX, and then it loads dwords one by one and adds all those dwords into EDX. Finally, EDX is moved into EAX, and this is the result. Nothing special here. In the beginning, we extract two arguments, one from ESP plus 4 and one from ESP plus 8. This argument is the length of the array, and this one is the address of the array. Assume that we somehow remembered that we want to save ECX to the stack. So we add those two instructions, push ECX and pop ECX. As a result, we are going to have to change those two instructions, which extract the arguments from the stack, into those two new instructions. We can see that the offsets has changed. We changed 4 into 8 and also 8 into 12. Think about what would happen if we wanted to change more things with the stack. Maybe we wanted to push another register, or maybe we wanted to refer to those arguments in the middle of the function somewhere. Note that ESP might change many times during the function. For example, maybe we call more functions, or maybe we want to store some values, or maybe push and pop for some reason. If we are going to use this method of taking ESP plus an offset, we are going to have to follow the current offset of ESP to be able to access arguments. We are going to have to follow ESP all the way in our function. We have to find out if somewhere there is some hidden push or pop, because we have to follow the current value of ESP. And this is not very fun. We don't want to start following all those pushes and pops just to find out how to access one of our arguments. We want to have a simple way to access our arguments. There is a solution. We could use EBP to remember what ESP was initially. And then we don't care about changes that happen to ESP. We just add this instruction in the beginning of our function, move EBP ESP. Now EBP is going to contain the initial value of ESP. And instead of using ESP in this syntax, whenever we want to extract the arguments, we are going to use EBP. Now, even that we have push ECX here, EBP will not change, and we can still use this syntax. We can even push another register here, and those two instructions will still work. Another simple addition to this piece of code would be to save EBP to the stack and then restore it in the end. We do this because maybe some other functions use EBP. Maybe, for example, the function that calls some nums, maybe there is such function, it also uses EBP. In that case, we don't want to change EBP because it will affect the external function. So first we save EBP to the stack, and in the end of the function we restore EBP. So this is the basic structure of a function. This is a very basic idiom. If you read lots of assembly code, you are going to see this everywhere. Almost every programmer, every assembly programmer that writes a function is going to begin the function with this construct and end it with this construct. Let's find out what really happens on the stack. Let's try to follow the code instruction by instruction and see how the stack changes. This is a drawing of the stack. As usual, we assume this direction of address goes, which means that the address 0 is somewhere here at the top, and the addresses increase as we go down. So let's begin. Assume that we are on the first instruction inside the function. At this point, we already have the arguments. The arguments were already pushed into the stack, and we also have the return address because of the call instruction that happened just before we got here. The ret address is the location where we want to go back when we finish with this function. This is what ret is going to use. Let's follow the instructions. We begin with push EBP, which is going to push EBP into the stack. We added here old EBP, which stands for the previous value of EBP. We say previous value because in the next instruction, EBP is going to have a new value, which is going to be ESP. Now EBP and ESP both point to the same location. Next we are inside the function. At this point ESP might change. In fact, it might decrease and be somewhere here in those locations. But EBP is not going to change. So we can rely on EBP to refer to those locations. For example, if we ever want to access argument 1 or argument 2, we will do it relative to EBP. We can't trust ESP because it could be anywhere. But we know that EBP keeps pointing on this location. If we count from EBP, we get that the return address will be at location EBP plus 4, and the first argument will be at location EBP plus 8. The second one will be at location EBP plus C, and the third one will be at location EBP plus 10 in base 16. So this is something that you have to remember. If I wake you up in the middle of the night, you should know those numbers. The old EBP could be found in location EBP. the return address could be found in EBP plus 4. Argument number 1 could be found in EBP plus 8. And argument number k is in location EBP plus 4 times k. Local variables. We might need some memory during function execution. Let me explain. Maybe we run out of registers for our calculation inside some function, and we want some memory cells. Or maybe we want to do some operations with strings, and we need a scratch pad inside our function. So we need some pieces of memory sometimes. We could use the global memory, but usually it is not a good option. We can point out maybe one important con, which is using the global memory is not very modular. We really want the function to be self-contained, and if we have to rely on some global locations in memory, things could get a little ugly. There are some other problems with using global memory. For example, you might have problems with multitasking or threading. This is also known as the function is not reentrant. I don't want to get into this, but those are just simple examples of why using the global memory is not always a good option. It is sometimes a good option, but not always. We could use the stack. And I want to show you how to do it. It is always good to have another location to store memory and to store data. This is how we are going to do it in a code. We begin with the usual prologue of a function, which is something like this. We just push EBP and then move ESP into EBP. Next, we want to keep 3 dwords on the stack for ourselves. We are going to do it by this instruction. We just subtract 12 from ESP, which is exactly 3 dwords. Then inside the function, we could use those dwords. We are assured that nobody is going to touch those dwords because ESP could only decrease. It could not increase at this part of the code. In the end of the function, we just add those 12 bytes back. And so we actually free them. Eventually, we exit the function as usual. We just pop EBP and use the ret instruction. Let's visualize this on the stack to see what really happens. This is a drawing of the stack, and as usual, we assume that the address growth is in this direction, which means that 0 is on the top and the addresses increase as we go down. Assume that we got to the first instruction inside this function, which is push EBP. At this point, the caller has already pushed some arguments into the stack, and we also have the return address. We got this return address from the call instruction. We can't see the call instruction here, but it was somewhere because this function was called. It was probably called using a call instruction, hopefully. The first instruction, push EBP, is going to push the old value of EBP into the stack. And next we move ESP into EBP, which means that EBP is going to point here. At this point, ESP and EBP point to the same location. Next, we allocate 3 dwords on the stack using this instruction, sub ESP 12. And basically this is just what happens. ESP is decreased by 12. or by 3 D words, and now it points to this D word. Conceptually, we can think about this location as the location of the local variables, or the local memory of the function. And those are the arguments. This is a pretty important picture. You should remember this picture. We can use EBP to get both to the arguments and the local variables. We can trust EBP to stay the same during the execution of the function, as opposed to ESP, which might move here somewhere. ESP could be decreased and increased during the function. However, EBP is not going to change. So we can rely on EBP to know the addresses of those locations, of the arguments and the local variables. A general formula to get into one of the variables is of the form EBP minus 4 times k. And as usual, if we want to access the arguments, we just have to calculate EBP plus 4 times r. As an example, the first argument is at location EBP plus 8. And this local variable is at location EBP minus 4. An important point to remember is that arguments are at positive offset relative to EBP. However, the local variables are at negative offset relative to EBP. Before we return from the function, we have some arrangements to do. First, we free the 3 allocated D words. This is going to be done just by increasing ESP. Whenever we want to free allocated stack space, we just have to increase ESP by the correct amount of bytes. And this is the effect which is going to be achieved. At this point, ESP and EBP again point to the same location. Finally, we pop EBP to restore it to the old value, and we return from the function. You probably noticed the local state is freed when the function returns, which means that local data lives a pretty short life. It only lives during the execution of the function. But when the function ends, the local data dies. It didn't really die, because the values are still here on the stack, but some other function might override those values. They are not allocated anymore. I mention this because you should understand that local data should not be used for objects in memory that live longer life. For example, you cannot create data on the stack that lives longer life than your function. The data on the stack, the local data on the stack, cannot outlive the function. When the function ends, the local data dies. This is a very important concept to remember. I want to add another comment regarding the kind of data that you want to keep on the stack. The stack is not that big. Therefore, you don't really want to keep very large things on the stack. There are other places to store very big objects. We are going to learn about those constructs in the future. The stack is for pretty small things. You can maybe store some array or some D words, but don't store megabytes of data on the stack. You will get in trouble.